Welcome to this lecture series in group theory. Last time we discussed the notion of symmetric groups and the general linear group. I will not recall those definitions because I don't really need them. What I need for this particular lecture is for you to know what is a linear map, what is an orthogonal projection, although this is optional, and how to multiply two matrices. And again, I don't want to recall the definitions of these things. Anyway, I assumed some basic linear algebra background, and in that I included the definition of linear maps and matrix multiplication. Orthogonal projections is a somewhat optional thing that you, even if you don't know it, it's fine, but it helps. Okay, so these are the problems, and now let us go to this lecture. So in this lecture we'll be discussing something called the orthogonal group of R2. So let me just start. So theta be any angle measured in radians, then the anti-clockwise rotation of R2 by the angle theta is defined as a linear map, which is given by the following equation. So this is this matrix, 2 by 2 matrix, so this is the definition, and you can expand this out. So this is cos theta, well, let me write x cos theta minus y sin theta, x sin theta plus y cos theta. So this is the definition. Although this is a very cheap way to define a rotation, the geometric picture is very clear. Geometric picture is just, suppose you have this particular vector. Rotation by theta is just the vector obtained by, actually rotating by theta. But one way to express it formally is this linear algebraic way. There is a purely geometric way to express this, but that takes time, and it's not the kind of thing that we want to discuss in this course. So I just took the cheap route because it's quick. Alright, and one can of course intuitively see that this thing, basically you first rotate by phi and then you rotate by theta, is nothing but rotating by theta plus phi, which is intuitively clear, geometrically clear I would say, but you can also use this definition, and it will be an exercise in trigonometry, high school trigonometry, to see that this is actually equal to that. Alright, so that's rotation. Another thing we want to discuss is reflections. So fix a line passing through the origin, call it L, and we will define the reflection of R2 about this line L. So geometrically it's very easy to describe. You take any vector v or any point in the plane v, all you have to do is just think of this as a mirror and reflect the point v about this this mirror. So you drop the perpendicular, whatever is this length, you travel in that direction one more time in the same distance, and you'll get the reflected point. So that's the definition, but there is a linear algebraic way to express it, so let me get into that. So we have this vector v, this is v, and let PL be the orthogonal projection onto L. So PL is a map from R2, well, R2 to R2, but the image of PL is L, and in fact this is the orthogonal projection. So what does it do? It takes any vector W and it gives you this guy. So this is the perpendicular that you drop, and it gives you that thing. That's the orthogonal projection. So how do we express the reflected point for V using PL? It's very easy. This thing is PLV, and sorry, this is a little bit longer. That thing is, this is PLV, so that thing is V minus PLV. So if I reverse this arrow, that becomes PLV minus V, right? And what I want to do, I want to put this arrow again and compute what that guy is. So it's just V plus that plus that. So PL of, SL, which is the map that I'm trying to describe. SL of V is V plus PLV minus V and then another PLV minus V. So that turns out to be equal to 2 PLV minus V. Right, so this is, I had written the same thing here. Basically, you define. I written it in one shot here. So SLV is equal to that, where PLV is the orthogonal projection onto L. So anyway, the geometric picture is very clear. The linear algebraic way to express it may at first sight seem mysterious, but it is not. Okay. And note that this holds, meaning if you take a point, you reflect, and then again reflect, you get the same point back. So reflection composed with itself is the identity map, which is to say that a reflection is its own inverse. So that should be clear. You can see this using this stupid equation, but geometrically it's immediate. Okay. There is a certain relationship between reflections and rotations, and this again, one can prove this identity linear algebraically just by feeding in the definitions, but let me do it geometrically. So L is some line which is passing through the origin, and theta is some angle. So we want to say that if you first reflect about the line, then you rotate the resultant point by theta, and then you again reflect by the line, you get that. This is same as that, so I can also write this is equal to SL T theta SL. We just commented that a reflection is its own inverse, so this is same as that. Anyway, so the thing that we want to say is that this three-step process is actually just a one-step process, which is rotation by minus theta, meaning rotation in the clockwise direction by theta. So let's see a proof of it. We fix some point P, which is, let's say, making an angle alpha with L in the anti-clockwise direction. Okay. So if we reflect P, we get some point here. Reflect P by L. Basically, we are computing SL of P. So SL of P is some point here, and let me show you the picture. Yeah. So we reflect, we get this point. And now we rotate it. Now we rotate it by theta, so we get something like that. So that is also something that we can show. Yeah. So once we rotate this, we get that point. And now we again reflect that guy by theta, about this line. So we'll get some point here. So that should be, yeah, that's visible now. Right? So this is our final thing. So let me label all this in the figure. So this is SLP. This is T theta SLP. And then this is SL T theta SLP. Right? So this angle is alpha, because if you reflect P, these two angles will be same, so that is alpha. This is theta because we rotated by theta. Alright? And therefore, if I join this line, let me join it with some other color, maybe blue. If I join this line, this angle is same as that angle. So that thing is theta plus alpha. Alright? But this is already alpha, and this is theta plus alpha, so this thing is theta. So this is theta. And so basically the point P sort of gets rotated in the clockwise direction by theta, and hence the resultant effect, basically this thing, is nothing but T minus theta of P. Right, so that's the proof of it. Alright, this is same as saying that T theta SL equals T minus theta SLT minus theta. So it's sort of like reflections and rotations commute, but not exactly, because there is this minus theta here. If there were theta here, then I would have said that they commute, but they don't, because just look at the details. All right. Another thing that we want to see is that how do two reflections behave. So if you compose two reflections, what do you get? And what we want to say is, okay, if we fix two lines, L1 and L2, and let's say they make an angle theta between them, and the transformation A is the composite of two reflections, one about L1, then about L2. And we want to say that actually the transformation is nothing but rotation by 2 theta. So this is very easy. Again, geometrically, one can do the linear algebraic proof just by writing down the equations, but let us see why this is true. So let me extend this L2 thing a little bit. Yeah. So we start with a point, let's say some point here. First we reflect it, we get that P prime, then we again reflect it, we get P double prime. So it's a little bit, yeah, like that. Anyway, it's not, the figure is not perfect, but who cares. So if I draw all these three things, whatever this angle is, let's call it x, then this is also x, because reflection behaves that way. And if this is y, then that is also y. So therefore, what is x plus y? X plus y is theta, because this is theta and x plus y is the same thing. So x plus y is theta, and this whole thing is nothing but 2x plus 2y. So therefore, p double prime is nothing but p rotated by 2 theta. So that's basically the proof. So we keep that in mind. If you compose two reflections, you get a rotation. Okay. And now we can define what we mean by an orthogonal transformation. So an orthogonal transformation of R2 is a linear map such that there exist finitely many linear maps B1 up to Bn. So there is some finite n, it could be 1,000, million, who cares. There exist finitely many linear maps with the property that, first of all, each Bi is either a rotation or a reflection. And second is that A is actually this composite. So if you can write A as the composition of finitely many rotations or reflections, then you call it an orthogonal transformation. That's the definition. And here is an optional remark. You can ignore this if you don't follow it. Is that orthogonal transformations of R2 are precisely the linear maps such that A star A equals identity. Now A star is the adjoint of A with respect to the standard inner product. So this is same as saying that AX AY equals XY for all XY in R2. And these brackets denote the standard inner product. So this was a very quick way to define orthogonal transformations, and in fact in higher dimensions this is how we do it. But in 2 dimensions there's a very descriptive way to do it, and that's what we did. So if you don't follow this comment, forget about it. But if you know a little bit of linear algebra, if you know about adjoints, inner products, etc., then you can take this as an exercise to prove that these 2 descriptions are actually the same. This is a very, very, in some meaningful description. It's basically saying that orthogonal transformations are those linear maps which preserve the inner product. So it's a very meaningful description that way. This is a little bit on the, coming out of nowhere sort of description. Okay. So the set of all the orthogonal transformations of R2 is denoted by the symbol O to R. O stands for orthogonal, 2 is for the dimension that we are in, 2 dimensions, and R is the vector, the base field, so to say. The set of all the rotations of R2 is denoted by SO to R. So this is also called the special orthogonal group. Special orthogonal. SO stands for special orthogonal. So first thing we want to note is that this is actually a group. SO2R is a group. And this is very simple. So we need to verify three properties. So group under what? Group under what binary operation? Under composition. Okay. So three properties we want to verify. First is associativity. This is clear because composition of functions is associative, so composition of linear maps is also associative. If you compose two linear maps, you get a linear map, so that's not a problem, So anyway, verify associativity. And two is existence of identity. Clearly, if you rotate by 0 degree, that's the identity map. Rotating by 0 degree means not doing anything. So that's the identity transformation. And third is inverse. So clearly, t theta composed with t minus theta is t minus theta composed with t theta is equal to t minus theta plus theta, which is t0, which is identity. So everything has an inverse, and therefore this is a group. More interestingly, the set of all the orthogonal transformations of R2 is also a group under composition. And let us prove this. So, well, again, this is actually very simple. The first thing to note is associativity, and here there's a little bit of a check, because if suppose you have, should I use T? I shouldn't use T. Let's say A is some, what symbol? Let's say B1 up to Bn, where each Bi is a rotation or a reflection, and A prime is B1 prime up to B whatever, capital N prime. Then what is A composed with A prime? This is nothing but B1 up to Bn, B1 prime up to B capital N prime, and each Bi and each Bi prime is a rotation or a reflection. So we have written this as a composition of finitely many rotations or reflections. So this is also lying in the set of all orthogonal transformations. So closure under, so this is not associativity. Basically, we are verifying that this is indeed a binary operation. Composition is a binary operation on on O2R. We should have checked that here also. That composition indeed is a binary operation. But if you compose two rotations, you get a rotation. That's what we commented when we wrote that this is equal to that. So I should have mentioned that here anyway. So composition is indeed a binary operation. Associativity follows because associativity holds for composition of any maps. So associativity, I leave you to check or convince yourself. Identity. Well, the rotation by 0 is indeed an orthogonal transformation. And this behaves as identity because if you compose this guy with any linear map, you get the same linear map back. So of course, if you compose this by any orthogonal transformation, you'll get the same orthogonal transformation back. So this is indeed the identity of O2R. And finally, inverse. So for inverse, what you do is if A is some orthogonal transformation and it is a composition of rotations and reflections, then just consider Bn inverse, Bn minus 1 inverse, so this thing one can easily verify is actually A inverse. That's not hard, and since each Bi is a rotation or a reflection, each of these guys are also rotations or reflections. If you invert a rotation, you get a rotation. If you invert a reflection, you get the same thing back. So it is again a reflection. So therefore you can write A inverse as a composition of finitely many rotations or reflections, and therefore this is also in O2R, and clearly, of course, that A inverse equals A inverse A equals identity. This goes without saying. Anyway, so this is also a group. So lastly, there is a very simple description of any member of the orthogonal group. Now we can legitimately call it the orthogonal group since we have shown that it is indeed a group. So here is the description. You pick any orthogonal map then either it is a rotation or it can be written as a composition of a reflection and a rotation. So it's not, you don't need to write, you don't need to use too many of these rotations or reflections. Just two, at most two will suffice. And here is the proof. So let me just show you the proof in a very simple case. Say A equals some reflection, then some rotation, then some reflection, and then some rotation. Let me just show you the proof in this particular example, and the general case will be very, very clear once you see this. So what we have is, this is S1. I will think of it that way, bracket this and T2. And now we'll use this property that S2 T1 is T1 inverse S2. Right, this is what we commented. Let me show you that equation. This one. Right, so rotation reflection is reflection and the inverse of the rotation. So that's what this is. This thing. So using that, we get this is equal to S1. Actually, what I want to do is this. There's nothing wrong with what I wrote, but this is the thing that I want to use. It's the exact same principle. So we have that, and let me just use that to write the above thing as this. So this is S1, S2, T1 inverse T2. Now this is a rotation, because composition of two rotations is a rotation, and this is also a rotation, because composition of two reflections is a rotation. We said that. So this particular one we were able to write as a rotation. Now if there were three reflections or an odd number of reflections in this sequence, then you will, by the same kind of pushing the reflections on one side and rotations on the other side, you will see that here an odd number of reflections will be there, and here some number of rotations will be there. So this part will be a rotation, while this part will have a reflection component. So figure it out. Just by the same kind of reasoning, you can show this. So that's that. So that's a very simple description to the set of all the orthogonal maps. And we will need this kind of description. I think we'll need this kind of description in the next lecture when we will discuss the dihedral group. The dihedral group is the reason why I'm discussing this orthogonal group. Otherwise, I would not have. All right, and dihedral group is a very important group. It's a very interesting example of non-abelian groups, and we'll learn about non-abelian groups in due time. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.